Sorry guys, my battery just died on the camera, so I had to get a fresh battery here. We're almost done. This is just the very end of the last example I'm going to show you. So instead of calculating the double integral of the curl of f, we're trying to calculate this line integral instead and use Stokes' theorem. Okay? But I threw a twist into this surface, which is I oriented the surface downward, which means that the corresponding boundary curve needed to be parameterized clockwise. We haven't done a lot of examples where we have a clockwise orientation, but here is one where we do need to use a clockwise orientation. So I put a minus sign in right at that spot there. Okay? So guys, we have, of course, our position vector, r of t. That just consists of putting these components into the vector. So I've chosen to parameterize the curve clockwise. If we parameterized it counterclockwise, that would be all right. But the answer that we get at the end of the day, we would have to change the sign of that answer. Okay? But anyway, I'm going to do it just counterclockwise from the get-go. So my r prime of t, we need the r prime of t for the dr, right? Let's see, that's going to be negative 2 sine of t, comma, negative 2 cosine of t, comma, 0. All right? And then I have to write my vector field in terms of t. Okay? My vector field is right here. So I'm going to put in everything into there. So we have, x squared y z in the first slot. That's going to be negative 8 cosine squared of t sine of t. And then in the middle slot we have y z squared. That's just going to be negative 2 sine of t. And in the third slot we're going to have z cubed times e to the xy. Oh, that would be e to the negative 4 cosine of t sine of t. Okay, there we go. We have to calculate f dot dr for the line integral, right? So that's the dot product of these last two vectors that we have up here. So when we dot these first two together, we're going to get 16 cosine squared of t sine squared of t. And when we dot these two together, we're going to get plus 4 cosine of t sine of t. And the last term goes away. We don't have anything left for that. Okay, so we're just about there. I think I can safely get rid of most of this. So the line integral is literally just the integral. T goes from 0 to 2 pi of this expression that we just came up with. 16 cosine squared of t sine squared of t plus 4 cosine of t sine of t, and then just dt. All right? So that's what we actually will end up with right there. Okay, I guess the best way to do this is, you might remember that there's a trig identity. So getting it set up is the most important part, by the way. This integral here, let me just start with this one. If you just use a u du on this, right, you're just going to get sine squared of t divided by 2, u squared over 2 in other words. And when you evaluate that from 0 to pi, to 2 pi, you're going to get 0. Because the sine of 0 is 0, and the sine of 2 pi is 0. So that really is not anything that you have to work very hard for. For this one, the best thing to do is to remember a trig identity, which is that if you take 2 cosine of t sine of t, that's actually just the sine of 2t. This is just a trig identity that can be useful. So if we square both sides of that, we're going to get pretty close to the first term of this integral that we have. Right? It's going to be looking kind of like that, yeah? Okay. So, but we're going to need to take out, so out of this 16, I'm going to take 4 outside, and then I'm going to integrate t from 0 to 2 pi of basically this, which is just the sine squared of 2t dt. All right? And there's a trig identity, again, for this one. If you remember, the sine squared of theta, right? Sine squared of theta is 1 minus the cosine of 2 theta, all over 2. Okay, so in this case it would be 1 minus the cosine of, well, 2 times 2t, which is 4t, all over 2 dt. When you integrate cosine, you're going to get sine again. When you plug in 0 and 2 pi into sine, you get nothing, right? So really the only thing that doesn't get canceled to 0 is this 4 over 2 here. So you just have a 2 basically times the integral of dt from 0 to 2 pi. I'm going kind of quickly through this part. It doesn't really matter that much. The final answer there is 4 pi. Okay. All right, so that is an example of Stokes' theorem where we were asked to calculate a surface integral, and we converted it to a line integral instead, okay, and did the line integral calculation. All right, well, that's about it. I have maybe one more example, but I'll save it for class on Tuesday as kind of maybe a warm-up problem or something. Let me give you one more little bit of extra credit here. I'm just going to tell you the last place I went out of the country on a vacation is probably my favorite place I've ever been in the world, which is the southern tip of South America. It has a very nice name. It is called Patagonia. So please write that down, because every time I see the word Patagonia, I smile and think about the good times that I had last winter when I went there on a vacation with my family. So, all right. So you've gotten a little bit of extra credit. Hopefully you know how to do Stokes' theorem and the divergence theorem, as well as calculating line integrals and surface integrals directly. All of that is really the meat of the vector field surface integrals. Of course, we also have the surface integrals of the scalar functions, which is a whole different thing. But for surface integrals of vector fields and line integrals of vector fields, a lot of that has been kind of touched on in this video. So I hope it was helpful. I'll be around. I'm here to help you guys. Best wishes with everything, and I'll see you all again soon.